AB calculus AB. I'm sorry, AB calculus BC. Unit 8, day 2 lesson. So we're going to keep working on the series. We're going to kind of review a little bit of what we talked about in the last lesson, sort of summarize some of those things. And so definition of a series is a sum of terms in a sequence. So generically A1, A sub 1, A sub 2, A sub 3. That's kind of a generic way of referring to you turn A sub in, which on the last assignment they use that. That's the open form. This is the closed form. So definition of a geometric series. So that's a series in general. A geometric series, each term is obtained by multiplying the previous term by the same number each time. Now that number we often refer to as R, and we call it the common ratio. We're going to be dealing a lot with geometric series. The formula for convergence of a geometric series specifically, and here's a closed form of a geometric series. Open form would be AR squared, AR cubed, AR to the fourth, and so on. The general term is AR to the n minus 1 plus ... So that's the open form. That's the closed form. This equals the sum, which the formula is A over 1 minus R. But this is if and only if the absolute value of R is less than 1. And the common ratio has to be less than 1. A equals the first term. R equals the common ratio. They call it the common ratio because you can figure out what R is anytime by taking any term and dividing it by the previous term. And it should always come out the same. So division, ratio, always the same, common. Okay, here's an example of a crazy looking closed form, but we could just plug n equals n in and see it's going to be negative 1 to 0, 0, 2 to the 1, 3 to the 0 is 1. So we're going to get 2 for the first term. And then when you plug in n equals 2, that's going to be a negative 1. So you're going to definitely get negative. And then you have a 2 squared is 4 over 3, 4/3. The next term, n equals 3, this negative is going to be raised to an even power, so it's going to be positive. And 2 to the third is 8, and 3 to the second is 9. So we could keep going with this. So this was n equals 1, n equals 2, n equals 3, n equals 4 is going to be negative. 2 to the fourth is 16, 3 to the third is 27. You could start to see the pattern here. The next one's going to be positive. It's going to be, the top's going to get multiplied by another 2. The bottom's going to get multiplied by another 1. And it's going to keep going. So that's the open form. Now, we could maybe write a easier to understand closed form, because this is a geometric series. The first term is 2. Each next term gets multiplied by 2/3, negative 2/3. Going to raise it to the n power. The first time we don't want it, so it's going to be n minus 1. That's the same thing. Now, we could write it another way. We could start n equals 0. You need to be able to do any of these. Sometimes they're given to you like this, sometimes like that. Now, if it's 0, then we're going to have a 2. It's going to be negative 2/3 to the n. That's it. That's the same thing. That will give you the same exact series. Now, a value is 2. The r value is negative 2/3. Is the absolute value of r less than 1? Yes. So we know it converges. The value it converges to, the sum, capital S, is usually what we use to reference that. The formula is a over 1 minus r. I'd write that down every time until you memorized it. 2 over 1 minus negative 2/3. Be careful with the extra negative. It's going to be plus plus. 2 over 5/3. 2 over 1 times 3 over 5. 6/5 is the sum. All right, let's try another one. This one is, now when you see a repeating decimal, on your next test, I'm going to give you one like this. And I don't want you to use the trick from AP Calc AB. I want you to treat it like a series. So the first thing is to do is to try and write it like a series. This is the same thing. 0.2 repeating is 0.2 plus 0.02 plus 0.002 plus 0.0002 and so on. So if you write it like that, you say, oh, this is a series. A value is 0.2, R value is 0.1, or you could write as a fraction 1/10. So is the absolute value of R less than 1? Yep. So we know it converges. And the sum is A over 1 minus R. So it's 0.2 over 1 minus 0.1. So it's 0.2 over 0.9. We don't want decimals in our fraction, so we're going to write as 2/9. Or instead, you could have put in 2/10 over 1 minus 1/10. And then that would be 2/10 over over 9/10. And that would be 2/9. Like that. All right. So just a little review. Now, today we're going to use our graphing calculator to start to see some cool things that we can do with this. So we're going to every day we're going to kind of build off what we've learned the previous day and take a little further. So we're going to do a lot of stuff with geometric series. There's something called a power series. And a power series is a geometric series, which we've learned. This is the value. What it does is a equals 1, the first term is 1, and r equals x. So instead of putting a number in for r, which is what we've seen so far, we're going to put a variable like x. So if you're to do that, the series is going to be 1 plus x squared plus x cubed. The common ratio is x. Okay? And I'm going to show you something crazy. We're not going to get there. I'm not going to show you where this comes from yet, but I'm going to tell you right now that this is equal to the function, the rational function, 1 over 1 minus x. I'll prove it to you. Okay? And that's kind of interesting now, but it's only if the r value, which in this case is absolute value of x, is less than 1. So we said, what I'm claiming is this series converges to this function. Okay, if you plug any value of x in here, it'll give you the same thing as this x. Now, let me demonstrate this on my calculator. That has funny spots on it and stuff, but that's all I got. I'm going to graph 1 over 1 minus x. And let's make the window -2 to 2, -5 to 5. So let's just start with that. So that is, that looks like a typical graph. It has a vertical asymptote at x equals 1, right? It has a horizontal asymptote at x equals 0. As x gets bigger, it goes to 0. Okay, so, and then the graph looks like this. If you plug in, 0, you get 1. If you plug in -1, you get 1/2. Plug in -2, you get -1/3, or you get 1/3. If you plug in 1/2, you get 2. So this is what that graph looks like. Okay, if you plug in 1.5, you get -2. If you plug in 2, you get -1. If you plug in 3, you get -1/2. So the other graph is kind of symmetric. It's the same shape. Looks like this. So I'm just starting with that graph. Okay. Now, this is called a power series. It's called power series because it has x's to powers in it. It's kind of like they call it a power function. It's a polynomial, right? It's a polynomial. Now, when I graph this, let me go back and I'm going to make this line dark, thick. Okay, so I changed that to that so it kind of stands out. So that's our original graph. Now, what I'm going to do is I'm going to start graphing just the partial sums of this function. So first time, I'm just going to graph the first 3 terms. So it's going to be 1 plus x squared, just the first 3 terms. And then I hit graph. So there it is. And it's kind of weird. It's not even close to this function, but it does get close to it right kind of around here, right? Which, by the way, is when x is between -1 and 1. It kind of in the middle there, it seems the closest. Let's do the next one. 1 plus x squared plus x cubed. So I'm going to put one more term on the partial sum. And let's see. So the first one, well, I'll graph it again. So there's the first one. So the first one was a parabola, and it kind of went like this, right? So this was, I'm going to try and make this look what I have on my graphing calculator. This is a big idea, okay? This is going to set up so much of what we're going to do this chapter, next chapter. So that was y1. This is y2, and then y3 is a cubic, which you expect. And it kind of comes in and hugs the graph a little closer, a little sooner. And then it does start to deviate from it, but not as bad as the other one. Okay? So what happens with more terms? More terms, this graph starts to become a closer match. Okay? Less terms, not as close. So, I mean, we could go in and do another one. 1 plus x squared plus x to the third plus x to the fourth. Let's graph it. So this one comes in and it starts, it holds on to it longer than the other two, right? It's closer to that dark line. So the more terms, but it's really only for a certain chunk of the graph. It's pretty close for when absolute value of x is 1, when x is between -1 and 1, which x is the r value of this geometric series. This is a geometric series with x in it. So when the r value is less than 1, absolute value, this converges towards this. Okay? Now this is kind of interesting, okay? But this is what we're going to use power series for. So this is a power series. Okay, that's what we call these, a sum and or difference of powers of x. So it's a bunch of powers of x being added or subtracted. Okay, The only thing that's happening is addition, subtraction, multiplication, right? Really just like addition and multiplication. And we can represent this function, which might not seem that complicated, with a polynomial. This is not a polynomial. This is a rational function. And we're trying to fit a polynomial to it. So these power series, they're polynomials, which is one of our most basic functions in math, right? Okay, we can create other power series that represent other functions from this mothership. Now, mothership, that was a Mr. Statham saying, essentially, this is where everything's coming from. Okay, this is the main one. And we can manipulate it by replacing x with other expressions, more complicated expressions with x, multiplying it, dividing it, differentiating it, integrating it. We can do all kinds of crazy things. So let me show you a couple things right here. This right here is close to what we have right here. Now, by the way, the other thing I want you to see this as, and even this right here, is that the sum equals a over 1 minus r, right? I mean, that's the formula right there, a over 1 minus r. If a equals 1 and r equals x, then you get 1 over 1 minus x. So now when we see a function like this, we think, oh, well, that's the sum. That's a over 1 minus r, which means that's the a value, and the r value is negative x. So this is almost like the last one. Now the terms, the first term is going to be 1, and then you're going to, that's the a value, right? The open form. This isn't the closed form. This is the sum. The open form would be the first term, and then times the r value, 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 and then times the r value. It's going to flip signs every time because the r has a negative in it. Okay, so that's the open form. And then we could write the general term right here, and then we could write the closed form. Now the general term here depends on where you start in. If we start at n equals 1, well, it might help to write n equals 1, n equals 2, n equals 3. It's going to be negative x to the n minus 1, right? Negative x to the n minus 1. Whatever goes inside your closed form is also the general term, the nth term. Okay? So this is called the open form. We were talking about this yesterday. This is the open form, and this is the closed form. And this is the nth term or the general term, and it shows up here also. Now, we could have written it a little different. We could start at n equals 0. Well, then that changes your general term in here, your nth term. So now it's going to be just to the nth power, same thing. So you can, I mean, we could start at n equals 10 if you want. That's weird, but you could. I mean, 1 and 0 are the most common starting values for n. Now check out what happens. If we integrate 1 over 1 plus x, which we know how to do, right? That means if we want to get the integral of this, we could actually integrate this polynomial. The antiderivative, the integral of 1 over 1 plus x, is the natural log of 1 plus x. Absolute value. So what I'm going to do here is I'm going to integrate both sides. Okay? If you integrate the left, you integrate the right, it's polynomial, it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6 plus ... We could even integrate the general term. What would the antiderivative of this be? Well, it would be negative x. You would add 1 to the exponent and then divide by the new exponent, right? Right? But an extra negative would pop out, so I think we need an extra negative on the outside. So you can actually get the general term by integrating the previous general term. Now, the closed form, if we start at n equals 1, it should look like this. It's going to be negative x to the n power over n. If n equals 1. Now, if n equals 1, we get a negative, and so we definitely need that negative, right? N equals 1. That would give us this series. If you plug 1 in, you get positive x. If you plug 2 in, you get negative x squared over 2. That totally works. Now, I mean, there's other ways of writing it. I mean, that's just from this. You could also take the approach of like, okay, well, usually if you look up here, the closed form of a geometric series usually has the first term times the r value to a power. I mean, you could do that. You could say, oh, well, the first term is x, and then the r value is negative x. And, well, actually, it's not even geometric anymore. The r value isn't the same number being multiplied anymore. So it's kind of weird. It's kind of like there's a geometric series on top, and you do n minus 1 because you want an x there, and then you're going to divide by n afterwards. So we started with geometric series that we got a power series from, and then we integrate both sides, and now it's creating other series that aren't quite geometric series. But like I said, you could even write it starting at n equals 0 instead. If you do that, then you're going to need, negative, I think you're going to need an n plus 1 on the top and then an n plus 1 on the bottom because you don't want division by 0. And if you plug 0 into this, it's going to be negative. You want it to be positive. So that would be another version of it. I mean, we could write tons of different versions of this. Now, there's something called the interval of convergence, okay? So convergence is when it works. And we pointed up there at the top, this is only, geometric series, which these are all based off of, only converge if the r value is less than 1, okay? And in this problem, both of these problems, the r value was negative x. So we have to make sure that the absolute value of negative x is less than 1. Now, this is an absolute value inequality. And I mean, you could do a little line check right here. When does x equal 0? When does, what's the border of when this is going to work or not work? It's going to be negative 1 to 1 and everything in between, right? Oh, this is like using that rule apostrophe from Calc AB with solving absolute value inequality. So you say, okay, well, it's at 0. We want to be 1 away from 0 in both directions. And we want it to be less, so it's going to be in between. So negative 1 to 1. So this is the interval of convergence. That means this function, this is kind of crazy. This polynomial, that's still a polynomial. This polynomial equals natural log. Okay, but it really only works for values of x that are between negative 1 and 1. Now, we'll usually write our intervals of convergence as an interval notation. You guys should remember how to do that. So that's interval notation. That means the same thing as this, but this is the interval of convergence. This is where this works, where we can represent natural log with just multiplication, addition, and subtraction, which is the basic things that your calculator can do. That's the basic things computers can do. They're processors. Multiplication, addition, subtraction, and division. That's it. So this is how your calculators represent more complicated functions. They represent it with polynomials. Okay. Today's assignment is out of your book, the Calc BC book, page 477. I want you to do exploration 1. It is required to get credit for the whole assignment. And then you're going to do these. The explorations pretty much lead you through some interesting conclusions. They help you along the way. I want you to do them. The next few days of assignments are going to have some of these on them. They are required. So go ahead and try the homework. Try the assignment. Check your odds in the back. Evens online if I put them online. Okay.